Thank you very much for all the opportunities to speak here, and thank you for coming. So today I will talk about the problem that was originally posed by Drinfeld, and then it was mostly solved by Tinkov and Kazhdan. So let me first give you some overview and history. So again, as before, there is not a lot of us, so please stop me, ask me. Yeah, I don't have strong agenda to get somewhere. Yeah, we will see how it goes. Okay, so let G be a Poisson Lie group. So it's a Lie group together with a bivector, but this bivector is not invariant, but it satisfies a different property. So pi is it's a Poisson bivector, and it's such that the map from G cross G to G is a Poisson map, the multiplication. Okay, so it's an example of a PoissonHopf algebra. To be more precise, the algebra of functions on this group, which you know that this is a commutative of algebra because these are functions on a group. Mm-hmm.
Okay. Is this bivector field uniquely determined by its value at the identity of the group?
So no, because the value is always 0, but it's determined by the derivative at the identity. No, like here you would get like, for the identity you will get that pi plus pi at the identity has to be equal to pi at the identity. But for simply connected Poisson Lie groups, this will be equivalent. You can get it from the derivative at the identity.
So the derivatives, is it like the structure constants or something?
Yes, this should give you the co-bracket. Because, yeah. It's a map from the Lie algebra to GUHG, right? The derivative.
So again, how is this pi determined? Can you say what are the data to get a bivector on a group which satisfies this?
Okay, so I can say now. So this category of Poisson Lie groups, which are one connected, so connected and simply connected, this is equivalent to the category of Lie bialgebras, of finite dimensional Lie bialgebras. I should write bigger. Okay, and yeah, Lie group gives you a Lie algebra, and the derivative of the bivector at the identity gives you the co-bracket. So I don't know how to write it. Yeah, I think right. So you take a vector at the identity. That is to say, so which is the same as G, and you act by it on the bivector. And this is an element of G, wedge G. So you get a map from G to G, wedge G. I think this is the correspondence, which will be so this will be the co-bracket. So we express it, so this is in coordinates, but it should be well defined because it vanishes in the identity. Yeah. Yeah. Okay. Okay, if you, in coordinates, this is something, and you can act on it on this function. And if you change coordinates, this is well defined, this because if the vector field acts on the Jacobi matrix, the result will be 0 because this vanishes at the identity. So this is well defined. Yes, sir, probably there's an invariant way to say it, but I don't know now. Yeah, but like, yeah, but like at the end, what you get? So let's say this is an element of the Lie algebra. So this has maybe. Okay, yeah. So this has two indices up, one index down. They are all indices in the Lie algebra, and they transform linearly if you change coordinates. Yeah, so this is the vector field at the identity, like with corresponding to the xk is an element of the Lie algebra. Which means you can take derivatives of functions. Okay, nevertheless, it should not be necessary to understand what I wanted to tell you. But it's true that these Poisson groups, they are the same as Lie algebras. So the Lie algebras are their infinitesimal. Lie bialgebras, they are their infinitesimal versions. Yeah. Okay, so the functions on a Poisson group, it's not just a commutative of algebra because there is also the Poisson bracket. So we have this C infinity of G, which is an Hopf algebra, yeah. Commutative of algebra. So you are familiar with this, with how C infinity of G is a Hopf algebra. Is it fine for? Mm-hmm. So yeah, that's a good question. So coproduct should be a map. So here we take some kind of completed tensor product. So this is actually C infinity on G cross G. Okay, and then coproduct on a function. This is a function which takes two elements of the group. So if you just plug them in, yeah, the coproduct is dual to product. So this is F evaluated at G1 times G2. Okay, but the Poisson, the bivector, it gives you a bit more structure here. So you also have a Poisson bracket. That is in some way, it is compatible with the multiplication of the group. Multiplication of the group corresponds to the coproduct. So this Poisson bracket is compatible with delta, and this means that delta is a map of Poisson algebras. And let me write this explicitly. What does it mean? And I will use this pictorial notation throughout the talk. So for me, I always, as Niels, I start from the diagram start at the bottom, go to the top. So the compatibility of the bracket with the coproduct. Yeah, this is clear. So this is C infinity of G, C infinity of G. Take the bracket and the coproduct. This is equal to the following. So you have two functions, you take their Poisson bracket, and then you apply coproduct on the result. The same thing as if you take those two functions, apply coproduct, so now you have 4 elements, and you pair these two with the bracket, and you just multiply these two as functions. Mm-hmm. This is a definition of a Poisson-Hopf algebra, exactly. Yeah, the question was whether this was a definition of a Poisson-Hopf algebra, and exactly. So let me write it down again. So H is, or a Poisson-Hopf algebra is an commutative Hopf algebra H with a Poisson bracket. This involves the compatibility of the bracket with the multiplication. It's a derivative and so on. That satisfies this identity. So you have seen that a Poisson group gives you a Poisson-Hopf algebra, and it is in some kind of category of, let's say, vector spaces, but with this different tensor product. This Poisson-Hopf algebra. Also, if you have Lie bialgebra, which it's almost the same, then you get a Poisson-Hopf algebra. UG is Poisson-Hopf. But it is in vector spaces, but vect op. Okay, so we need to take opposite here. For example, you know that it's the coproduct on UG, which is co-commutative. So if you see it as a Poisson algebra, as a Hopf algebra in vect op, it will be the product which will be commutative. But it's best not to get too much into those ops.
These Poisson-Lie groups, they give rise to these Poisson-Hopf algebras. Is there also a way going back, or?
Not always, no. In some way, yes, I forgot the name of the theorem. But there's a theorem, right, which says that commutative Hopf algebras, they correspond to functions on group. Yeah, and then the Poisson, yeah, if you have a Poisson bracket on functions, it should give you the bivector easily. You can just evaluate, yeah, for example, evaluate on. But this is more general because this makes sense in any, let's say, symmetric monoidal category where you can add morphisms because you need addition of morphisms in this. So let me write it down, maybe this remark. So these Poisson-Hopf algebras in any R-linear, this is a ring, R-linear symmetric monoidal category. Because if you go through the list of axioms of a Poisson algebra, you just need tensor products, and you need, and there are these flips, these operations.
And what is Poisson in this case?
So
what is the Poisson bracket in this?
So Poisson will be a map from, let's say, H, tensor H, to H, which satisfies all the necessary properties. So it satisfies Jacobi, it satisfies the Leibniz identity with respect to the multiplication, and it satisfies this identity.
And down here, so how does it work, this Poisson-Hopf algebra?
So, so then, because this is in vect op, what you actually get? You get a map like this. And it comes from the co-bracket, right, which goes from G to G cross G, and it's extended by this axiom. This one, but you have to turn it around. Yeah, I don't want to. I don't remember the detail of the extension, but you can extend the co-bracket to a map like this. No, so this is the Poisson bracket, but it's in the vect op. So okay. In vect op, we need to get a map that goes from UG, tensor UG, to UG. Right? That satisfies some properties. So this should be a Poisson bracket. This should be a Poisson bracket, right? But a map like this in vect op is the same thing as a map from UG to UG tensor UG. Because, yeah, this is the opposite category, so morphisms are just maps going the other way around. Mm-hmm.
So the UG is the G.
This is the universal, sorry, yes, I should have said that. Yeah, that's the universal enveloping algebra. Okay.
And the product is also like the product, or how, no, I'm a bit confused.
Okay, so
UG?
the product in the vect op will be the coproduct of UG.
Oh, but that's the Poisson bracket, you said.
No, the coproduct of UG, is defined as x is sent to x tensor 1 plus 1 tensor x. This is the coproduct. And the product is so this is the product in vect op, and the coproduct in vect op is just the usual multiplication of UG.
So what is delta because of op, it becomes just a normal multiplication, and the Poisson bracket,
yeah,
because it's op, it becomes a coproduct delta.
Yeah, so maybe
small delta.
Yeah, so this is the product in vect op of U product. Yeah, let's just product in vect op, and this is the coproduct in vect op. Okay, and there was a question posed by Drinfeld, how to quantize, whether it's always possible to quantize these things. Mm-hmm.
Is there also so you wrote on at the blackboard above a certain rule between Poisson bracket and the coproduct.
Yes.
So is there a similar thing with Poisson bracket and product?
Yeah, this is, so when you have a Poisson bracket, it always should be a derivative in each of its arguments.
I see.
And as usual, Poisson brackets in normal field, in normal quantum, in the classical mechanics.
Okay, thanks.
Yeah, that was. Okay, so, a special, if H is a Poisson-Hopf algebra, so special part of this data is just an commutative algebra with Poisson bracket. So you have H, M, the unit, and the Poisson bracket. So this is just a commutative algebra with a Poisson bracket. And now you can... Yeah. No, of the algebra. So it will be like the identity element.
Like 1?
Yes. Like on C infinity G to the constant function equals 1. So you can ask whether you can quantize this, and you know that Poisson algebras are quantized to associative algebras. So. But there is more structure there. There is also this coproduct and the co-unit. There's also the antipode. So by definition, quantization of a Poisson-Hopf algebra H, so this will be formal power series. Let's call them MH. We start as M, plus there is H bar times M1 plus H bar squared times M2. The same for delta. The antipode is also deformed. Maybe I should put this in. These are not powers, of course. These are just indices of the operations. And you also have the unit, and the co-unit which stay the same. This is. So these are such. You have such operations, such that H with these operations, or it should be power series in H bar with this MH delta H epsilon SH is a Hopf algebra. And of course, we want the multiplication to give you the Poisson bracket after dequantization, as in usual deformation quantization, such that, this corresponds to AB is equal to M1 AB minus M1 BA. And this is the first order of the commutator of MH. And so this was solved for Lie bialgebras by Etinkov and Kazhdan. What I'm going to show you now is a different solution. It makes some things clearer and more conceptual, but yeah, it is a different solution.
So if you look at the universal invalidity algebra and you take the quantum group construction, right? Can you say something to that? Like if you consider quantum groups, right?
Yeah. So yeah, I can try to remember. So you should just take Q equals e to h bar, and that should be the quantization.
No, but then you say it's the same thing directly. This is not the case, right? Because you have a Poisson structure here.
Okay, so in quantum groups, there's some kind of, I think there's some kind of canonical choice of a Poisson structure which is not mentioned. It's this R matrix which gives you the Poisson structure. So and that is somehow, I don't know, but I thought that there is a unique one up to multiple or something, or maybe there is not, but then one needs to specify.
Maybe my question is more like, why do I consider this instead of directly using quantum groups?
So this is, okay, so quantum groups, you start with a Lie algebra, but there is also some choice which is sometimes not mentioned, and this gives you a Lie bialgebra, and then the quantum groups quantizes the Lie bialgebra. This is, here what I talk about is, this is quantization of a general Lie bialgebra and more. This is quantization of a general Poisson-Hopf algebra in any symmetric monoidal category. You don't like the answer?
I'm half convinced, let's say.
Okay, so let me start with something that might look familiar. So let's just keep for now just the co-algebra part of the. So let H delta epsilon be a co-algebra. Okay, then we can do this bar or co-bar construction. I don't know which one, I'm sorry. And it's the following thing. It's a collection of, let's say, the unit field and H, second power, and I should have written in a different way. It's like this. And you have these maps, and there are more maps. I will not say what they are, but now I will say in a different way. So this co-bar construction, what it gives you is a functor from the simplex category, okay? To some category, let's just write C for any symmetric monoidal category. And then this K will be just replaced by the unit of the category. Okay? So probably you know, or yeah, maybe it will be more standard to do this for an algebra, and then you would have a contravariant functor, so it would be a simple shell object in C, right? But, okay, so I claim that for any algebra you can craft such a functor. So let me give you an example how is it defined. So objects here, these are just, so I will write them as sequences of dots. Okay? So usually this one will be called 0, this one could be called 1, this one could be called 2. So, and morphisms are, if you see this as an ordered set, morphisms are maps that preserve order. So for example, from 2 to 3, you have such a morphism, or from 2 to 1, you have such a morphism. Okay, so this. Okay. Yeah, this is the simplex category. You can also say this is the skeleton of the category of finite ordinals. Ordinals, like ordered sets. Because you just, yeah, for any number, you have one, and morphisms should preserve the order. So what is forbidden would be a morphism like this. So this is not allowed. Okay, and
So that's the simple category.
that's the simplex category, delta. Yes. Mm-hmm.
But then there are several morphisms between them.
Yes, yes. And let's call this functor nh.
And on the right-hand side, just to remind us, what is this SSE?
So this will be just any symmetric monoidal category.
So what is roughly?
You should think of vector spaces. So it should be a category where you have a tensor product between objects. And there is a natural isomorphism between A tensor B and B tensor A. This is the symmetric part.
And the M is for model?
For monoidal. There's like monoidal product there instead of tensor. Okay, so let me give you an H. Oh, sorry, the other way. Sorry, first I should define it on objects. I'm sorry. So nh just on, if you take n dots, this will be just h power n minus 1. Okay? So you should think of putting one h to every space between those dots. For those of you who know the bar construction, you should see h as a one object category where with arrows as objects of h. So these are all, let's say, all decomposable arrows. But if you don't know, then never mind. Okay, so this is a definition. And for example, the map I wanted to show you here. So we should go from H to H tensor H. And this one will be the coproduct.
And another one, or several?
This one? Or?
From 2 to 3 again, but different one.
So this will be like combinations of units, for example, and coproduct. Like if one goes to 1, 2 goes to 2. That should wait. Let me think. Yeah, now I'm confused. Sorry. Now maybe there should be, you need a bit more structure here. But it will all become clear in a minute. I will give a general definition. Sorry.
But this is not just the identity or something?
No, because you should go from H to H tensor H. Yeah, and yeah, sorry.
Not just zeros.
No. Okay, now I will give you a general definition, and probably I missed something, and then you need a bit more structure. Extend to the Hopf algebra. Okay, so the goal is to extend such construction to Hopf algebras. And to capture Hopf algebras, we will need to replace this simplex category. Okay, so delta, the simplex category, is replaced by something I will call braided, I will call Precomposing. Okay, so let me describe Precomposing. So as objects, the objects are the same, plus you also add an empty object. So objects are just 1, then dot, then 2 dots, 3 dots. Okay. And morphisms. So these will again be pictures as before. But now you allow these these maps to cross. And there is BR, which means that this will be a braided monoidal category. So the morphisms will be pictures which look like this. Or they can also collide. So morphisms are pictures like this. And there is a relation which says the following thing, that if two strands collide, you can just untwist them. Yeah. Like, if there are more, then you can permute them in any way you want. So what way is that braiding? So, for example, such a map you cannot untwist because they do not collide. Yeah. So obviously you have a map from delta to Precom, right? Because these are just special cases of those pictures. The maps here, they are just special cases of maps here.
So this is the thing that basically corresponds to the Yang-Baxter equation, right? In the setting of quantum groups, in some sense, right?
Yeah, in some sense, yes. But
yes. Like if you consider the R matrix, right?
Yeah. Okay, and now, so this is Precom, and now I want for a Hopf algebra H. I will define a functor that I will call it NH again, that goes from this category, Precom, to again any symmetric monoidal category. So if you know, you can also say it can actually go to a braided monoidal category. So you can talk about Hopf algebras in braided monoidal categories. But you can just think of it as a usual Hopf algebra over some field, and this is just vector spaces. That's good enough. Okay. So as before, on objects, we added one object, this one. So this is just the unit of the category. And on n dots, you just send it to h power n minus 1. And okay, and now I will give you an example. Sorry, 1, 2 of NH evaluated on a specific morphism in this category. Okay. I want to do this one. Okay, so here there are 4 dots, so it should come from h power 3 to h power 2. So this should be a map from h power 3 and h power 2. And maybe, yeah, this is also the reason why I talk about it here, but maybe it helps if you think of it of some kind of topological quantum field theory. So you have a Bordism, or not a Bordism, but some evolution between 2 dots, 4 dots and 3 dots. And to this we assign, which is a morphism in some category, and to this we assign a morphism in a different category. So Hopf algebra gives you some kind of functor, which one can see as some kind of case of a topological field theory. So let me give you the prescription. Okay. So we So we start with those 4 dots on a line. And now we look at this picture. So what happens is that this dot, it will move here, and this dot will move behind it. So let me try to write what happens. So let's try to see what happens with this line, okay? So this dot just doesn't do much. This dot will move here. This dot will move behind. So this line, what it does, it goes first here, then it goes here, and finally it visits the last dot. What did it? Ah, yeah. So because these 2 dots collided, you see them as being 1 dot made out of 2 little dots which almost collide. Let me do this. Yeah, so this is this dot. This one goes under.
The difference between under and over?
Yeah.
What happens if it went over?
So it would give you a different morphism.
But the same picture up to now?
No, so which one? This one if it went over? So it would actually, so it would be different. So this thing would be braided the opposite way, the top. Yeah, it would, I don't want to. So it would go like this, this, this. So this would be the top, otherwise. Yeah, because so maybe if I this one. Yeah, this one goes to the front, and this one is kind of in the back. Yeah, you see, yeah. So this should really be. You should see this as a 3-dimensional picture. And now what we do, we put H on each of the things in the middle. That was the original prescription. And now here we want to get 2 H's. So what do? We just draw a line between those new dots. Okay. Okay, what happens now is that, for example, this line, this H, it's intersected twice. So we start, but we have to use the coproduct, because from one H we need to get 2. So we draw a picture like this. Okay. This H, it goes here. And this H, it goes here. So these you should see as living on this 2D surface, which is kind of deformed. So these lines, they are on the surface. And let me redraw this without the surface. So you had H, H, H. You use the coproduct. And these two, they collide in the following way. So they do this, this, and this. And there are 2 more steps. So first one, this one, if you were going along this line, you would turn 180 degrees, because what the surface does, it goes like this and goes up. So you need to apply antipode to the power of the number of turns. And here there is just 1 turn. So we apply the antipode of the Pavol Ševera. And there is one last thing. These are in a vertical position. You need to put them in a horizontal position. And the convention is that you turn like this. So you turn like this. So if we turn these in this way, obviously this one is Yeah, this one is on the top. Then you have the middle one. And this one is on the bottom. So this is a diagram for a map between h power 3 to h power 2.
Can you write it with elements now?
So, or I can write it, let's say, let's first just do, it will be delta tensor S tensor identity on H. Yeah, this is, let's say, you get here. Then there is some kind of braid. So I will just write beta. It's composed of these braidings in this symmetric or braided monoidal category. So this is the braiding corresponding to this braid, which is here. And then you do identity on H, tensor product of 3 elements into. So this is the last step. You just multiply those 3 together, and this one just stays the same.
Because the associative doesn't matter.
Yeah, you could also write you could also write 1 tensor n. Okay. So this is a construction. So for each of algebra, we get a functor like this. Do we get all such functors? No, we don't get all such functors, but it's pretty easy to characterize all those functors which come from Hopf algebras. So that's a question. Which n come from some h. So one thing is that this n should be braided. So this is just, okay, braided lax monoidal functor. Lax. So you probably know from topological field theory that the functor should be monoidal, but usually one should just, okay, it should be set strong monoidal, but usually all monoidal functors are just strong monoidal. And let me tell you what the difference is. So you have a functor f, or in this case n, between monoidal categories. Then it is lax monoidal if you have a natural transformation like this. That satisfies some axioms. And it is strong monoidal if this mu is an isomorphism for all A and B. Usually you require, in TFTs, you require that Z of A is equal to Z of A. So here, sometimes you require equality, and this would be called strict monoidal, but every strong can be strictified. But here we only require map in this direction, so that's a slightly different thing. But this is not the only condition. There is another condition which we call nerve condition. And this basically, I will not write it down. It's nothing complicated, but it ensures that n of n dots is isomorphic to n of 2 dots power n minus 1, right? Because that's what we want. That's how we define the functor. N of 2 dots was defined to be h. So we want and this was defined to be h power n minus 1. So I can write this as a theorem. So the category of Hopf algebras in C so there's one thing I didn't mention, and that antipode should be invertible. But antipodes are not invertible in only very degenerate cases, but I should say that. Okay, so the category of Hopf algebras in C, this is any braided monoidal category, is equivalent to the category of functors, which are braided and lax monoidal from Precomposing to C that satisfy the nerve condition. Okay. So this is a theorem. Now, you could ask about commutative Hopf algebras or Poisson-Hopf algebras. So for the shortness, I will just tell you about Poisson-Hopf algebras. Poisson-Hopf. So this needs to be some R linear category now. And this is the same, here is the same thing, braided like monoidal functors. But instead of Precomposing, you need to replace this somehow. And the replacement is called infinitesimal, yeah, okay, just ecom. Again, with the nerve condition. And so morphisms in ecom, there things can cross, like this, for example. But you add a generator to the morphisms, which is called a chord. Okay, it's another category. And now, natural question is how to get from Poisson-Hopf to Hopf. But luckily, by Drinfeld's work, there's a functor from here to here, from Precomposing to ecom, almost. There are some details that I will tell you. So let's say you choose a Drinfeld associator. Okay. So it allows you to do two things. Okay, the first one is that from ecom, if you have a functor from ecom to C, now we need to, there is one assumption we need to make, that the ring R, it contains rational numbers, because Drinfeld associators, they can be chosen with rational coefficients. Okay. So what you can do here, you can replace this category by the same category with the same morphisms, the same objects. Sorry. But morphisms are formal power series of the morphisms of the original category. And here you also replace the associativity axiom. And the claim is that, okay, if we had a functor ecom C, then f extended h linearly is also a functor, and if we had a braided lax monoidal functor here, f will be also braided lax monoidal. Just need okay. So there is one thing, and the other thing is that there exists a braided strong monoidal functor from this Precomposing to this category, which I called icom h bar phi. Okay, so finally the quantization. No. Let H be a Poisson-Hopf algebra. So you craft from it the functor and H that goes from icom to C. You can just extend the functor h bar linearly to such functor. But the Drinfeld associator, it gives you another functor here. And this composition, by the theorem, you just need to check that it satisfies the nerve condition, but it does. This composition is the quantization. Yes. Because it's a functor from Precomposing to some braiding model category, so it gives you a Hopf algebra. Okay, thank you.